bit about the 5 pillars of sustainability that Boeing has. And what I would like to do today is go a little more in depth into operational efficiency, particularly looking at air traffic management. Really, what can we do to optimize the operation of an aircraft in order to minimize fuel consumption, minimize cost, and minimize emissions to really promote sustainability using the capabilities that are already in the system right now. So we can go to the next slide. So really, operational efficiency, one of the key advantages here is that we don't need to worry about the deployment of any additional infrastructure. We don't need to worry about research and development. We don't need to worry about introducing new elements into the aviation system. What we're looking to do is utilize what capabilities, what onboard equipment the aircraft itself carries, and how do we use that effectively to minimize the environmental cost of operating that aircraft. Next slide. Now, by our calculations, depending on the room for efficiency gains, depending on some of the operational gains that we can make, this can actually lead to up to a 10% reduction in fuel consumption and emissions. So this is something that for very low cost, again, we're really trying to leverage what capabilities we have on the aircraft itself. That's a very significant gain that we can do. And as we introduce new elements into the system, things like SAF, things like fleet renewal, we can retain these benefits because whether you're operating this on a 15-year-old aircraft or one that came off the line 15 days ago, you're going to get these performance benefits no matter what level of efficiency you're operating your aircraft with. As long as you've got these operational efficiency, and particularly these air traffic management benefits, no matter how, what other benefits, you're going to retain these up to 10% CO2 emission savings. Next, please. So there's really 3 core elements of operational efficiency. So maintenance and retrofit, this would be making sure that we're adhering to proper maintenance schedules for the aircraft. It can even be washing the aircraft after flight to minimize any kind of drag just with the dirt and grime that builds up over the course of an operation. This can also be doing things like retrofitting an aircraft to incorporate the latest savings. So things like taking older 737 or 76 aircraft and putting winglets on them. Things that we can actually change the physical structure of the aircraft in order to reduce the fuel consumption, increase the efficiency of that aircraft. Now, flight and fleet and airport operations, these are some of our digital management tools that we can look at, making sure that we are dedicating the right aircraft for the right mission, things that we are really optimizing the schedule itself of the aircraft. The flight and traffic management, air traffic management, this is really making sure that the actual operation of that aircraft is as efficient as possible. That we are really looking at from gate to gate, when that aircraft is in operation, whether it's in the surface, whether it's in the terminal environment, whether it's in the en route environment, that we are minimizing the emissions and fuel consumption that the aircraft is doing. Next, please. So just a bit of an overview right here. We can go ahead on to the next. Really some of our driving principles with using air traffic management for sustainability. What we're trying to do is minimize the energy that that aircraft takes to conduct its operation. So this means that we are looking to reduce throttle, reduce fuel. But if we are really making sure that the aircraft itself is doing as little work as possible in order to perform its operation, particularly in phases like climb out and arrival where we are burning the most fuel, we have significant gains to reduce fuel consumption, reduce CO2 emissions, reduce operating costs. That there's certainly a financial component to this in addition to the sustainability benefits that this really promotes. Now, one of the big things that we really promote is that many of these gains are not based on an airport or an ANSP acquiring new capabilities, acquiring new infrastructure. We're really looking to leverage what capabilities are already on board the aircraft. That whether it's using CPDLC or datacom in order to reduce frequency congestion, whether it is using RMP navigation capabilities in order to make sure that we are flying the most efficient flight tracks profile, whether it's using ADS-B type surveillance in order to get certified surveillance coverage in areas that are previously inaccessible by radar so we can increase throughput and capacity and we're not delaying aircraft, for example, flying through oceanic airspace where we were previously reliant on non-radar procedural separation. Again, all these capabilities are carried by the aircraft itself, So we're not looking to add new elements into the system that require new cost, new investiture. We're saying these elements are already there. How do we use them effectively? Now, when we get to these systemized operations, we're looking at a wealth of benefits. Certainly, we have the sustainability benefits. Reduced fuel consumption, more efficient operations means reduced CO2, reduced fuel costs, multiple benefits for the airlines as well as the general public, whether they're flying public or not. But also we're looking at a systemized operation is also an efficient operation. What we'd like to say is predictable and repeatable. That once you have these systemized operations, from an airline's perspective, you essentially know how things are going to work because you're flying a predefined path. Now, this also has benefits when it comes to capacity, when it comes to throughput, that when you're a air traffic controller, instead of tactically vectoring or having a little bit of unpredictability in the system, you know what that aircraft is going to do. If you're a pilot, you know what this flight procedure, you know what this operation is going to do. So now instead of having that tactical intervention from the pilot's perspective or the air traffic controller's perspective, you're now operating as part of a system rather than an active element of that system. That also promotes efficiency by building in efficiency into that system to begin with. Next, please. As we all know, this is a very, very basic element right here. The global aviation system is incredibly diverse. Airports around the world are different, regulators around the world are different, airline operations are different from airline to airline. But the one element that touches all of these systems is the aircraft itself. So really when we're looking to optimize air traffic systems, we want to make sure that we are fully leveraging the one common element no matter where you go in the world. No matter if you're flying a flight that is 30 minutes in the air or 15 hours in the air. The aircraft itself is always going to be consistent no matter how many elements of the air traffic management system you touch. No matter how many countries you fly through, no matter how many airports, how many regulators, how many ANSPs, the aircraft is going to be the common element. So if we can optimize the performance of that aircraft across all these elements of the system, that's when we will see significant performance benefits. Next. And there are a lot of different elements that we can really look to optimize, a lot of advanced operations that really take advantage of the avionics capabilities of the aircraft. This is just a small sampling from destination to origin, and it really even begins prior to the departure of the aircraft, making sure we're doing an optimized schedule, airport collaborative decision-making to reduce ground congestion and really facilitate an efficient departure and arrival flow into and out of airports from a planning purpose. Now, on the surface, we certainly have things like reduced engine taxi, we have efficient taxi paths, we have surface congestion management. Climb out, we have things like continuous climb operations. We have, when we get to the in-route environment, things like real-time weather and wind updates to pilots. We have things like trajectory-based operations. And then during arrival, we can leverage RMP capabilities. We can fly continuous descent. We can fly closed track procedures. We can even look to advanced operations like established RMP. And then once we're on the ground again, we can look at reduced engine taxi in. All kinds of things that each element individually can provide significantly reduced emissions, and they leverage the capabilities, again, that are already on board the aircraft. Next. So fundamentally, we're looking to get away from that old red track. Really, a lot of the elements of the air traffic system that are still considered global best practices are very, very dated. ILS is the latest and greatest technology that the 1970s have to offer. RMP really is the greatest technology that the 1990s had to offer. But now that we're seeing such a wide deployment across particularly commercial air fleets, we now have the ability to get beyond this inefficient, frequent level flight segments, multiple stops and starts when you're doing your descent profile, to now do this very predictable, very consistent descent operation that really provides a significant savings, again, in some of the most aerodynamically inefficient phases of flight. That if you can optimize that performance and you can really look to get the best performance out of that, kind of akin to last mile delivery when we're talking about a global logistics operation, if you can optimize this kind of last 5,000 feet and last 25 nautical miles of flight, you can do significant savings for your overall flight efficiency. And again, what we're looking to do is predictable, reliable, and efficient. But altogether, we're looking for boring operations, that we don't want the pilots to be excited when they're having to fly a very challenging stick and rudder approach. We want to build efficiency into that system, so day after day after day after day, we can see that efficient performance out of what were previously things that were spiking our fuel consumption, spiking our emissions, really contributing to some of the negative impacts of the aviation industry on the global carbon emissions. Next, please. So what we see on the left is kind of the previous general legacy design base, particularly the final approach capabilities of an airport. We're looking at old vectors like ILS to RMP, vectors to RMP, or vectors to ILS. But again, we're looking at level altitude segments at very low altitudes. We're looking at kind of rigid and inflexible designs where we don't have the ability to avoid noise-sensitive areas. We don't have the ability to get around some of these areas where the effects of aviation might be felt more. We have a much longer flight track that is longer, not only longer distance, that's more wear and tear on the engines, but it's just more flight time, that it's more time in the air, more time creating emissions, more time burning fuel. Now, when we go to a operational efficiency type airspace, this is where we can leverage things, again, like RP capabilities, and this is where we can have shorter flight tracks. We have certainly reduced track miles. We also have design flexibility. If we have a noise or emission sensitive areas, we can design around that, where we don't necessarily have to worry about some of these fixed ground-based infrastructures. And also, we don't have to worry about the regulatory policies and standards that are set out at the ICAO level and then enforced at the national level. What we can do is use the standards that support the application of these new, more efficient flight procedure design concepts and be a lot more flexible in our designs, again, to optimize efficiency and to minimize aviation's impact on the general public. Next. So this is just kind of an example of how we can take a legacy operation and we can minimize its fuel consumption, but we can also minimize its impact on the general public. So this is a set of conceptual procedures for the Seattle airport in the United States. And what we see on the right side, of the screen are the standard current methods of vectoring traffic into an ILS final approach in Seattle. This is the standard operation. So what we see right now is a lot of low-level flying. It's certainly it's an inefficient flight profile that we are either stick and rudder flying this, or we are constantly updating the FMS in order to get these flight tracks and these flight profiles. But we can also see that we're exposing a very, very high number, hundreds of thousands of people to noise exposure. Now, this does promote throughput, but it does not utilize what is actually deployed in the system right now. So if we look and really say, okay, even on the earliest vector turn, we're still exposing 172,000 people to the noise of each arrival. But if we can put in an RMP Zulu position with an RF turn, all of a sudden we're burning significantly less fuel, and we are exposing maybe a third of the people, if not a quarter or even 20% of the people, to the noise of that aircraft. So in this case, sustainability and environmental impact is certainly the reduced fuel consumption, the reduced CO2 emissions, but it's also the reduced environmental impact, noise, just the general smoke and smog, and the overall impact of aviation flight operations on the general public. You can also see some of the fuel benefits that this is saving. Over the course of the year, 25,000 metric tons of fuel. That's the equivalent of taking 5,400 cars off the road for a year. That is a significant savings based on, again, utilizing the capabilities that are on the aircraft itself. Next slide. So that's some of the conceptual operations, but what does this actually look like when we start to deploy this into the aviation environment? Not just the conceptual nature of some of these procedures, but if we're actually going to implement real-world operations, what's the performance benefits? Next slide. So one of the initial ways that we really saw a benefit of this was at the Denver airport in the United States. This was one of the first established on RMP operations that was actively flown. What this does is replace the traditional vectors to ILS These are the tracks that you see in red with a RMP. Basically, what we're doing is using the new ICAO standards that support the use of RMP as a means of providing precision approach capability, and we are replacing the existing vectors to extended downwinds on ILS. Now, what you see in red is a day's worth of traffic into the Denver airport. What you see in green is actually the same number of flights that are flying the RMP approach. This shows just how repeatable this operation is, that the capability on the aircraft is capable of flying a very precise and very repeatable flight track. This operation was deployed in 2018. In the first year, about 40% of arrivals into Denver flew this approach. The fuel savings and costs for the first year was about 46 million US dollars. That was 800 pounds of fuel per approach. That was 32 nautical miles of reduced flying distance, about 10 minutes of reduced flying time. In 2024, 70% of arrivals into Denver flew these RMP approaches. So we're seeing an almost double uptake in just 6 years of this operation being flown. Now, in addition to flying in Denver, we're starting to see this around the world. In the United States, Los Angeles and Houston are now flying established RMP. In Canada, Toronto and Calgary are flying RMP. Beijing is completing flight trials at Beijing Capital to fly established RMP. So we're now really seeing a global adoption of this new operation. Now, there are ICAO standards to support this. There's the SWAR, Simultaneous Operations on Incident Runway, as well as the RMP established manuals. So this is a perfect example of how we can get real-world performance benefits by using the capabilities that are on board the aircraft. Next slide. Another thing we can see is how we can use RMP capabilities in order to minimize noise exposure. These are a series of approaches into the San Francisco airport in the United States. The longer track that you see is a vectors to ILS track, which again provides safe operations, but it also provides environmentally impactful operations. As you can see, these tracks go over the urban cores of both San Francisco and Oakland. We're exposing a lot of people to noise. However, if we use a RMP RF turn and then we do a vector to a GLS, what we have is the ability to concentrate the vast majority of this noise exposure and environmental impact over the bay. And the joke we like to say is fish don't have phones, so they don't call to complain about noise. People have phones, they call and complain. So if we could utilize just some of the natural areas of the natural environment around an airport. Now it doesn't have to be water. If we have terrain areas with limited residential impact, if we have industrial areas, even if we have things like highway or train corridors, being able to use the natural and even man-made elements surrounding an airport in order to minimize the environmental impact of flight operations can provide significant benefits. Now, obviously that goes outside of the efficiency benefits of some of these RMP procedures. So what we don't see in this top-down procedure is that RMP turn, continuous descent, minimal level segments. We're flying a much more efficient continuous descent procedure that reduces fuel consumption, reduces CO2 emissions, reduces cost. Next slide. Now, if we look at a broader impact, we have our live flight multi-region trajectory-based operations. What this does is allows en-route operations to respond to evolving conditions to fly the most efficient flight track possible. This was a live flight demonstration that was conducted in 2023, and this was done in conjunction with the Federal Aviation Administration, the Japan Civil Aviation Bureau, AeroTi, and CAS from Singapore. And this was a live flight demonstration that essentially had a filed flight plan route from Seattle to Singapore. And midway in this flight, we simulated an event which required an active reroute of this aircraft. And this was meant to test a real-world, real-time data sharing between the aircraft, between the airline, and all of the relevant ANSPs. And this allowed the ANSPs to very quickly receive a new flight plan from the onboard information detecting capabilities of the aircraft. It allows that aircraft to file a new flight plan to either take advantage of maybe there's better wind conditions at a different altitude, maybe there's better fuel efficiency conditions if they could reroute south. Maybe there's weather events that they need to respond to. But now, instead of essentially sticking to that predefined route because we're dealing with multiple air navigation service providers, we now have the ability to quickly share and quickly get approval from all of the ANSPs that are on this route of flight to approve this new trajectory. So now we can optimize the en-route performance of aircraft and respond to evolving conditions, and again, look to reduce our fuel consumption, reduce our emissions, and reduce our CO2 on a very, very long segment of flight. This would be thousands of nautical miles of flight that we can optimize our fuel consumption on. Next slide. So this is just a series of examples from gate to gate, essentially, that we can really look to what can we do to optimize the performance of an aircraft at various stages of the flight. Next slide. Starting at the departure gate. So this is where we can do things like use airport collaborative decision making. We can do things like effective route planning, making sure that we're dedicating the right aircraft to the right route, making sure some aircraft are more suited to mid-range to long haul, some aircraft and some configurations are more suited to short haul performance. So really making sure that we are optimizing our aircraft performance prior to the actual operation of that aircraft can provide significant benefits for reduced emissions. Next slide. Now when we're taxiing out, doing things like surface congestion management, even doing staggered departure times by a minute or two in order to reduce the time that an aircraft is burning fuel while taxiing. Looking towards the future, we look at things like digital taxi or taxi bot, using things like ASMIGs and in-aircraft traffic displays in order to mitigate congestion before it happens. Anytime you have to start and stop, that's additional fuel consumption. So if you can have just kind of like a continuous descent, if you can have a continuous taxi with minimal stops, you can significantly reduce emissions while you're on the ground before that flight operation even starts. Next slide. Now, when you are in your climb out, we can do things like optimizing the climb performance and the takeoff performance of that aircraft. So optimizing when gears up, optimizing how we're using our flaps, optimizing thrust in order to facilitate an efficient climb out. Continuous climb is a huge element right here, that if we can minimize our level segments and climb out, and we can climb a slow continuous climb, that is less strain on the engine, but that's also less thrust on the engine. So we are significantly reducing our emissions, we're reducing our fuel consumption there. Also, if we can do things like feed real-time weather information to pilots, that can also, they are the ones who can adjust and adapt, and we can combine these with some of our other capabilities that we were just looking at, things like trajectory-based operations at the local level or the international level, in order to maximize the performance of that aircraft. Next slide. Now, when we're in the en-route phase of flight, the longer the en-route phase, the more opportunity we have to optimize that flight. Now, a lot of this can be using kind of the big data analytics, that we have a lot of aircraft that are operating in the en-route environment. These aircraft now more and more have the ability to collect data in real time and feed that back to airline operations centers, feed that back to centralized resources, and really calculate a lot of the data on what are the optimal flight conditions based on current observations. So we can take weather, we can take wind, and we can calculate, is there a more efficient aircraft altitude this aircraft can operate in? Now this is where we actually get to, if we can start utilizing more and more of our aircraft capabilities, it provides us more and more opportunities for sustainability. So let's consider, for instance, oceanic airspace. The prior way of operating in oceanic airspace in non-radar environments, where we had predefined tracks and we were reliant on HF radio, we were reliant on procedural separation. However, if we start looking at the aircraft capabilities, we can use things like space-based ADS-B to provide surveillance. We can use performance-based communications and even satellite-based communications, where we may not have that same latency. We may have some latency issues that are not present when we're looking at terrestrial standard radio communications, but we're certainly increasing the performance over HF radio. Also, if we do things like RMP routing, as opposed to using the the standard non-radar flight corridors that were the standard in oceanic airspace, we have a little more flexibility in how we actually route aircraft. But we combine all three of these, all of a sudden the aircraft is getting us in what was previously a non-radar environment. We have surveillance capabilities, we have communications capabilities, and we have navigation capabilities. Now, these may be slightly degraded from what we would consider the normal and terrestrial airspace, but they far outperform non-radar capabilities. So maybe we can get down to 15 nautical miles of separation. But in a non-radar environment, if we require 80 nautical miles of separation, and now we have the capability of using navigational capabilities and surveillance to potentially fly a different route that is not bound by a non-radar flight corridor, we have the ability to respond to a wide range of evolving conditions that can maximize, again, if we're looking at a trans-Pacific flight, that is something that can give significant performance benefits that if we did not utilize the capability of that aircraft, would have been completely unavailable to us. Next slide. Descent, this is where, again, we have some significant room for performance benefits. The use of RMP to facilitate continuous descent, the use of RMP to facilitate closed track arrival procedures into airports, and then the advanced performance capabilities of RMP-AR that can facilitate things like establish RMP, RMP established, or any of those other advanced operations can provide significant benefits because they really have the ability to eliminate a lot of those step-down descents. They have the ability to eliminate a lot of those low-level segments. Anytime you're flying low, anytime you're flying level, you're obviously increasing fuel consumption. Using the performance capabilities of the aircraft itself really had the ability to optimize a very fuel-inefficient phase of flight. Next. And then arrival, again, just like on departure, optimizing the configuration of the aircraft. This can be based on conditions, this can be based on weather, airport elevation, ambient temperature, that there's a number of ways that we can really look to make sure we are operating that aircraft. Even marginally difference can give significant fuel performance benefits, that if we know we can wait maybe 15 seconds later to deploy flaps, maybe that buys us a few kilograms of fuel savings, but multiply that over hundreds of arrivals a day, over 365 days a year, and all of a sudden we are now talking big fuel savings, big emission savings, increased sustainability. Next slide. And then finally, taxi in. If we can facilitate single engine taxi, if we can shut off one of those engines fairly short after landing, if we can use, again, that same service congestion management that we saw in the departure phase of flight, if we can optimize taxi paths in an airport to minimize congestion, minimize conflicts, minimize stops and starts, that's another way that we can really significantly increase our efficiency, again, while the aircraft is not even in flight, while we're operating that aircraft. Next slide. So what are we doing as a company to really facilitate this? Boeing is an active participant in the global air traffic management and operational efficiency ecosystem. Next slide. So we offer a wide range of partnerships that we certainly do airport and airspace optimization. That's really where the benefits of the air traffic management really is concentrated. And we know how our products operate, we know what the aircraft are capable of, and we really want to make sure we're working with all of the stakeholders in these systems to make sure that we are really getting the best potential performance. And we want our airline partners to know that when they take delivery of a Boeing aircraft, we are going to support them in getting the highest level of performance out of that aircraft. And we're not just going to say you're now reliant on what the limitations of the system you're operating is. We want to be able to say, we will work with you to optimize that system to get the best possible performance out of that aircraft. Environmental impact analysis, this is also goes hand in hand, that it's not just about utilizing the CNS capabilities of that aircraft, it's really making sure that we are using them in a way that minimizes the environmental impact of aviation. That when we're reducing fuel consumption, there's an economic benefit, but we really want to make sure that we're being good stewards of the environment we operate in. And we want to make sure that we are reducing emissions, we're reducing noise. To the greatest extent possible, we want to reduce and mitigate the impact of aviation on the general public in every element possible. And then finally, ATM modernization. This is really making sure that the global ATM system is capable of using these evolving conditions and capabilities that are now carried by the aircraft itself. That we don't want to continue to operate on legacy systems that they certainly may be safe and they may provide the services we need. When there's room for improvement and we can continue to optimize, we want to make sure that we are supporting ANSPs and regulators around the world to really take advantage of the capabilities that are now carried by aircraft. So we have a long history of really working in the global ATM environment. Dating back to 1994, when we started partnering with the Civil Aviation Authority of China, as well as Air Traffic Management Bureau in China, to really work to make sure that the air traffic management system is capable of really accepting the increasing number of foreign carriers that were coming into China at the time. Now, our air traffic management support has expanded and is now in multiple different domains. You can see that we are helping to push we're really helping to push the envelope on technologies, on regulatory standards, so we can use some of these new aircraft capabilities. Our Eco Demonstrator program has tested and proven a lot of new ATM operations in flight. And then, of course, there's partnerships with airlines and ANSPs around the world. Next, please. We also have our Operational Efficiency Handbook. This was a document that was published last year. It is now available to any Boeing customer, but it provides guidelines for a wide range of sustainability programs that are not just in air traffic management, but in flight and fleet management and retrofit. Really, it gives hundreds of examples and hundreds of potential means to reduce the environmental impact of aviation and to optimize the performance of aircraft throughout the fleet. This is something that we are actively promoting. This is something that is available to all Boeing customers. If you would like help accessing this document, please come to me, come to any of our colleagues here at Boeing, and we can help you get access to this document. Now, this is just a small sampling of some of the operators and some of the ANSPs around the world that we either have past collaborations with or active collaborations with. You may notice that on this map, we have Malaysia Airlines and we have CAM. So later this month, we will be publicizing the results of a performance optimization study, and hopefully what we will have is a new means of operating arrivals into Kuala Lumpur that we have forecast will have significant fuel savings benefits. This is, again, by using the capabilities that are on the aircraft. This was done with close coordination with CAM, and we'll be releasing jointly with CAM the details of this study very shortly. And I will say that we are very pleased with the results. CAM is very pleased with the results. So watch the news and you will really see some very interesting examples of how we can look to optimize the performance of aircraft within an existing system, and really how we can reduce fuel consumption, reduce cost, and reduce the environmental impact of aviation by using the equipment that aircraft carry. Next slide. So really, what to take away from this? Air traffic management operational efficiency is really unique amongst the means of achieving aviation sustainability. That we know things like SAF, fleet renewal, advanced technologies, they are all going to provide dividends for years to come. But air traffic management can provide benefits today. This is not something we have to wait on. This is not something that we need to deploy the infrastructure for. And while we're really striving for other elements of the sustainability infrastructure, we can start working on air traffic management enhancements now. We have the capabilities, the technologies are deployed throughout the environment, and what we've seen is significant opportunities for fuel and emission savings throughout the world. And these benefits will be retained as we integrate more of these advanced elements of sustainability. So as we increase SAF, we can apply operational efficiency and air traffic management procedures using SAF. We can apply these new optimized procedures with new aircraft, with new technologies, and we can retain and expand upon these benefits. So again, what we have is sustainable aviation now, and we have sustainable aviation tomorrow. Again, the highlights of this: utilize the capabilities of the aircraft. We have communications, navigation, and surveillance capabilities that can really push some of these sustainability goals and really unlock significant performance benefits. Again, this is really a way to increase the performance of the system without needing to acquire significant infrastructure. The infrastructure is already there. It's just flying at 35,000 feet instead of based on the ground. We really want to promote this integrated systems philosophy that what we're trying to do is really build efficiency into a system and then have that system be the standard means of operation. If we can design that efficiency and then just repeat that operation, that's where we see some, again, the repeatability of these benefits. The benefits are pretty extensive. We've got increased capacity, decreased flight deck workload, decreased controller workload, decreased noise and environmental impact, but critically, decreased fuel consumption, decreased fuel costs, decreased CO2 emissions, increased sustainability, and decreased environmental impact of aviation. Next slide. So that's a very high-level pass of air traffic management. This is something that we are working on currently here in Kuala Lumpur in Malaysia. Again, stay tuned for the news. By the end of this month, we're going to really promote the benefits of this study, and we are very pleased, and we hope you will be as well. So thank you very much for your time. I appreciate the opportunity.
All right, Mr. Garrison, thank you so much.